Hello everyone and welcome. I'm Pubali Sarkar, an assistant professor in the Department of Computer Science and Engineering. Today I'm excited to introduce you to our topic, circular linked list. In this presentation, we'll explore what a circular linked list is, how it works, and why it's important. We'll cover its structure, some key operations, and real-world applications. So let's get started and dive into this fascinating area of data structures. Let's take a closer look at what a linked list actually is. A linked list is a type of data structure that allows us to store data dynamically, meaning we can add or remove items easily without needing to predefine the size. This flexibility makes linked lists very efficient for managing data that changes frequently. In its simplest form, a linked list consists of a series of nodes, where each node contains some data and a reference to the next node in the sequence. Think of it like a chain. Each link points to the next, allowing us to traverse through the data step by step. On the slide, you can see the typical structure starting with a null pointer, which indicates the end of the list, and a header that points to the first node. This setup is fundamental because it helps us keep track of the beginning of the list, especially when we need to add or remove elements. Throughout this presentation, we'll explore how this simple structure can be used to build powerful and flexible data management solutions. Let's take a closer look at linked lists and some of their key features. First, you'll notice there is a pointer called the header. This header points to the very first element or node in the list. Think of it as the starting point of the list, guiding us through each element sequentially. Now, these nodes are connected by pointers, which means each node holds a reference to the next node in line. This creates a chain-like structure, making it easy to traverse from one element to the next. At the end of the list, the last node points to null, indicating that we've reached the end of the list. This null pointer is essential because it signals where the list terminates. One of the most flexible features of linked lists is their ability to grow or shrink dynamically during the execution of a program. Unlike static arrays, linked lists can expand or contract as needed, which makes them very adaptable to different data storage requirements. You can make the linked list as long as necessary without worrying about pre-allocating memory. And because of this dynamic nature, they only use as much memory as they need at any given time, avoiding waste. This efficiency in memory usage, combined with their flexibility, makes linked lists a powerful data structure for many applications. They are especially useful when the size of the data set is unknown or changes frequently, aligning perfectly with the overall theme of adaptable and efficient data management. Now let's talk about the circular linked list. In this type of list, the key thing to remember is that the pointer from the last element in the list doesn't point to nothing or null. Instead, it points back to the first element. This creates a circle, which is where the name comes from. Imagine having nodes labeled A, B, and C. The pointer from C, which is the last node, points back to A, the first node. This setup allows us to traverse the list in a continuous loop without reaching an endpoint. The head, of course, is the starting point of the list, and because of the circular nature, once you reach C and move forward, you're back at A. This structure is useful in scenarios where you want to cycle through data repeatedly, like in round-robin scheduling or buffering systems. Understanding this concept helps us appreciate how linked lists can be adapted to different needs, especially when continuous cycling is required. Let's talk about the circular linked list. Think of it as a variation of the linear linked list, but with a twist. It can be either single-linked or double-linked, but the key difference is that there are no null values at the end to mark the termination. Instead, every node points to the next node, and crucially, the last node points back to the first node, which creates a circle. Because of this structure, there's no clear starting or ending node. The entire list is connected in a loop. This means that from any node, you can traverse the whole list and come back to where you started, making it quite flexible for certain applications. When you traverse a circular linked list, you typically go through the nodes once until you reach the starting point again. This makes traversal efficient, especially in scenarios where you need continuous cycling through data. Also, it's interesting to note that a circular linked list can be implemented using both singly and doubly linked list structures, giving you options based on your specific needs. Overall, the circular linked list is a powerful variation that emphasizes continuous, circular data traversal instead of linear progression. Let's talk about operations on linked lists. When working with linked lists, there are several key operations that form the backbone of how we manipulate and manage this data structure. First, there's insertion, which allows us to add new elements at various positions, whether at the beginning, the end, or somewhere in the middle. Then, there's deletion, where we remove nodes, making sure to update pointers correctly to keep the list intact. Searching is another important operation, finding a specific element by traversing through the list. And finally, updating involves changing the data stored in a node without altering its position. These operations are crucial because they highlight the flexibility and efficiency of linked lists, especially when compared to other data structures like arrays. Understanding these operations helps us see why linked lists are so useful in scenarios requiring dynamic memory allocation and frequent insertions or deletions. Throughout this presentation, we've emphasized how these operations support efficient data management, and now you can see how mastering them unlocks the true potential of linked lists in real-world applications. Now, let's explore the operations we can perform on a circular linked list. First, creating a list involves establishing the initial node or nodes that form the structure. Once the list is created, traversal allows us to visit each node in the circle, which is essential for many operations like searching or displaying data. Insertion is a key operation, and in a circular linked list, we can insert a node at the beginning, which updates the head and maintains the circular link, or insert at any position within the list, providing flexibility for dynamic data management. Deletion is equally important, and we can delete the first node, which involves reassigning the head, or delete a node from the middle, which requires carefully updating the previous node's link. Deleting the last node involves adjusting the node before it to point back to the head, preserving the circular structure. Counting the total number of nodes helps us understand the size of the list at any point, which is useful for various algorithms. Lastly, revering the list is an operation that changes the direction of all links, effectively flipping the list, which can be helpful in certain applications. Overall, these operations make the circular linked list a versatile data structure for managing cyclic data efficiently. Now, let's take a closer look at how we create and traverse a circular list. First, we define our basic node structure, which includes an integer data field and a pointer to the next node. This structure is the foundation of our linked list. In the main function, we start by initializing the head pointer to null, indicating that the list is initially empty. We then prompt the user to enter the total number of nodes they want in the list. After receiving the input, we call the createList function, which is responsible for building our circular linked list based on that number. Once the list is created, we use the displayList function to traverse and display the contents of the list. This process demonstrates how we can efficiently navigate a circular list where the last node points back to the first, enabling continuous traversal without reaching a null pointer. The key takeaway here is understanding how the list is created and how traversal works in a circular structure, which is essential for many applications requiring continuous or cyclic data processing. This concept ties into the overall theme of understanding different types of linked lists and their practical uses. Let's walk through the process of creating a circular linked list. First, we define a function called createList, which takes the number of nodes, n, as a parameter. We start by declaring some variables, I and data for input, and pointers prevnode and newNode to manage the nodes as we build the list. Now, the key point here is that we only proceed if n is at least 1, since creating a list with 0 nodes doesn't make sense. We begin by creating the head node using malloc, which allocates memory for the first node. Then, we prompt the user to enter data for this node, and store that data in the head's data field. We also set the head's next pointer to null initially and set prevnode to point to the head, so we keep track of the last node as we build the list. Next, we enter a loop to create the remaining nodes from 2 up to n in each iteration, we allocate memory for a new node, prompt the user to enter data for this node, and store it. We set the new node's next pointer to null, then link the previous node next to this new node, effectively chaining them together. We then update prev node to point to this new node, so it becomes the previous node for the next iteration. Once all nodes are created, the crucial step is to link the last node back to the head, making the list circular. This is achieved by setting prev node's next pointer to head. This creates the circular structure that is fundamental to circular linked lists. Finally, we print a message indicating that the list has been created successfully. So the key takeaways are how we dynamically allocate nodes, link them in sequence, and then connect the last node back to the first to complete the circle. This process is essential for understanding how circular linked lists function and how they differ from linear linked lists. Let's take a closer look at how we traverse a circular linked list. In this example, we use the displayList function to print all the data in the list. First, we check if the list is empty by seeing if the head pointer is null. If it is, we simply print a message indicating that the list is empty. If not, we start from the head node and initialize a current pointer to traverse the list. We then enter a do-while loop, which ensures that we visit each node at least once. Inside the loop, we print the data stored in the current node, then move to the next node by updating the current pointer. We keep track of the node count with the variable n, which increments with each step. The loop continues until we circle back to the head node, completing one full traversal of the circular list. This method is essential because it highlights how circular linked lists differ from linear lists. They loop back on themselves, so we need a condition that stops the traversal once we've returned to the start. Understanding this traversal technique is key to effectively managing circular linked lists in your data structures toolkit.